Welcome to the first learning outcome, where we study kinematics, the science of how things move. Over the next few slides, we'll describe motion using graphs and the constant acceleration equations, building it up step by step with plenty of worked examples. Kinematics is all about describing how objects move without worrying about what's causing the motion. To keep things simple, we model an object as a particle, imagining all of its mass squashed into a single point. We'll learn to read gradients and areas from motion graphs and to use the constant acceleration equations, often called the SUVAT equations, including motion under gravity. Every idea comes with a worked example you can copy and practice. Let's get the vocabulary straight first. Displacement is the distance in a stated direction from your starting point, a vector measured in meters. Velocity is the rate of change of displacement, again a vector, measured in meters per second. Speed is just the size of the velocity with the direction stripped away, so it's a scalar. And acceleration is the rate of change of velocity, measured in meters per second squared. Here's a useful split. Vectors carry a direction as well as a size. Displacement, velocity, and acceleration are all vectors, and we usually show their direction with a plus or minus sign. So 5 meters to the right, or 9.8 meters per second squared downwards. Scalars, on the other hand, have size only, things like distance, speed, and time. No direction is attached to them. A few habits will save you a lot of trouble. Always work in SI units, that's meters, seconds, meters per second, and meters per second squared. Before you start a problem, pick one direction to call positive and stick with it. A negative velocity then simply means motion the opposite way, and a negative acceleration means the velocity is decreasing. And do keep your units consistent, converting kilometers per hour into meters per second whenever you need to. Let's look at displacement-time graphs. Time goes along the horizontal axis and displacement up the vertical one. The key fact is that the gradient, the steepness of the line, equals the velocity. So a steeper line means a greater velocity, a flat horizontal line means the particle is standing still, and a straight sloping line tells you the velocity is constant. Let's work one through. A particle moves in a straight line, sitting at 2 meters when time is 0, and at 14 meters when time is 4 seconds, joined by a straight line. Velocity is the gradient. That's the change in displacement divided by the change in time. The displacement changes by 14 minus 2, which is 12 meters, over a time of 4 seconds. 12 divided by 4 gives 3, so the velocity is a steady 3 meters per second. Velocity time graphs work in a similar way, but they tell us more. Time is on the horizontal axis and velocity on the vertical. This time, the gradient gives you the acceleration, and here's the really useful part. The area underneath the line gives you the displacement. A flat line means constant velocity with 0 acceleration, and a line sloping down to meet the axis shows the particle slowing to a stop. It's worth comparing the two graphs side by side because they're easy to mix up. On a displacement time graph, the gradient gives velocity, and the area underneath means nothing useful. A flat line means the particle is at rest. On a velocity time graph, the gradient gives acceleration, the area underneath gives displacement, and a flat line means constant velocity. Keeping those straight is half the battle. Let's find an acceleration from a velocity time graph. A straight line rises from 5 meters per second at time 0 to 25 meters per second at 8 seconds. Acceleration is the gradient, the change in velocity over the change in time. The velocity climbs by 25 minus 5, that's 20 meters per second over 8 seconds. 20 divided by 8 comes out at 2.5, so the acceleration is 2.5 meters per second squared. Now let's use the area to find a displacement. A car travels at a constant 20 meters per second for 6 seconds. So on the graph, that's a flat line at 20 from 0 to 6 seconds. The area beneath it is simply a rectangle, and its area is height times width, 20 times 6. That gives 120, so the car's displacement is 120 meters. Let's pause and check what's stuck. On a displacement-time graph, what does a flat horizontal line tell you about the particle? What physical quantity does the gradient of a velocity-time graph give you? How would you find displacement from a velocity-time graph? And if a velocity-time line slopes downwards to meet the time axis, what's happening to the particle? Have a think before you carry on. When the area under a velocity-time graph isn't a simple rectangle, the trick is to break it into shapes you already know. Split the region into rectangles, triangles, and trapezia. A rectangle's area is base times height, a triangle's is a half times base times height, and a trapezium's is a half times the sum of the two parallel sides times the height between them. Add all the pieces together and you've got the total displacement. Let's try a journey in 3 stages. A train speeds up from rest to 20 meters per second in 4 seconds, holds that 20 for 6 seconds, then slows back to rest in 5 seconds. The first stage is a triangle, a half times 4 times 20, which is 40 meters. The middle stage is a rectangle, 20 times 6, that's 120 meters. The last stage is another triangle, a half times 5 times 20, giving 50 meters. Add them up, 40 plus 120 plus 50, and the total displacement is 210 meters. Now we meet the constant acceleration equations, usually nicknamed the SUVAT equations. There's one important condition: they only work when the acceleration is constant. They tie together 5 quantities, so given any 3 you can find the others. The letters stand for S, the displacement, U, the initial velocity, V, the final velocity, A, the acceleration, and T, the time taken. The real skill is spotting which 3 values a question hands you. Let's be precise about those 5 letters. S is the displacement during the motion, in meters. U is the initial velocity, right at the start of the timed motion. V is the final velocity, at the end. A is the constant acceleration, which stays the same throughout. And T is the time interval over which the motion is measured, in seconds. There are 5 equations, and each one deliberately leaves out one of the quantities. The first is V equals U plus AT, which has no S in it. The second, S equals UT plus a half a T squared, leaves out V. The third, S equals VT minus a half a T squared, leaves out U. The fourth, V squared equals U squared plus 2AS, has no T. And the fifth, S equals a half times U plus V, all times T, leaves out A. Choosing the right equation is really a matter of bookkeeping. List the 5 quantities and write in the 3 you already know. Mark the one you're trying to find. Then pick the equation that leaves out the 5th quantity, the one you neither know nor want. Substitute your values, rearrange to solve, and finally check the units and ask yourself whether the answer looks sensible. Let's find 2 unknowns at once. A particle starts at 4 meters per second with a constant acceleration of 2 meters per second squared for 6 seconds. For the final velocity, we use V equals U plus AT, so 4 plus 2 times 6, which is 4 plus 12, giving 16 meters per second. For the displacement, we use S equals UT plus a half a T squared. That's 4 times 6 plus a half times 2 times 6 squared, so 24 plus 36, which comes to 60 meters. Here's one where the time isn't given. A car accelerates uniformly from rest, so U is 0, up to 30 meters per second, over a displacement of 90 meters. Because we've got no time, we reach for V squared equals U squared plus 2AS. Putting the numbers in, 30 squared equals 0 plus 2 times a times 90, so 900 equals 180a. Divide, and a is 900 over 180, which is 5 meters per second squared. A lovely special case is motion under gravity. Near the Earth's surface, any freely falling object accelerates downwards at about 9.8 meters per second squared, which we call g. So all we do is replace the a in our SUVAT equations with g, or with minus g if we've chosen up as positive. We ignore air resistance in this model, and as always choose a positive direction and keep your signs consistent. Let's drop a stone from rest and let it fall for 3 seconds, taking g as 9.8 and calling downwards positive. Since it starts from rest, u is 0, the acceleration is 9.8, and the time is 3 seconds. For the speed, v equals u plus at, that's 0 plus 9.8 times 3, which is 29.4 meters per second. For the distance, s equals ut plus a half a t squared, so a half times 9.8 times 3 squared, which is a half times 9.8 times 9, giving 44.1 meters. Now let's throw a ball straight up at 19.6 meters per second, taking upwards as positive and g as 9.8. The clever step is to notice that at the very top the ball is momentarily at rest, so its velocity there is 0. Using v equals u minus gt, we get 0 equals 19.6 minus 9.8t, so t is 19.6 over 9.8, which is 2 seconds. For the height, v squared equals u squared minus 2gs gives 0 equals 19.6 squared minus 19.6s. And solving that, s is 384.16 over 19.6, which is 19.6 meters. Time for another quick check. Which SUVAT equation would you choose if you knew u, a and t but wanted to find s? Why must the acceleration be constant for these equations to work at all? What value do we use for g, and in which direction does it act? And at the very highest point of a vertical throw, what is the velocity? Mull those over before moving on. Let's head off some common slips. Don't confuse displacement, which is a vector, with distance, which is a scalar. Watch your signs because up and down need opposite ones. Never use the SUVAT equations when the acceleration isn't constant. When you square a term, square the whole thing, not just part of it. Keep your units in and don't mix kilometers per hour with meters per second. And remember, on a velocity time graph, the gradient is acceleration, not displacement. Let's draw the outcome together. Graphs and equations are just two ways of describing the very same motion. On a displacement-time graph, the gradient gives velocity. On a velocity-time graph, the gradient gives acceleration, and the area gives displacement. The 5 SUVAT equations handle any constant acceleration problem. Motion under gravity is simply SUVAT, with the acceleration set to 9.8 meters per second squared. And throughout, define a positive direction and keep your signs and units tidy.